Good morning, good afternoon, good evening, wherever you may be. Thanks for joining our Stantec webinar series today. A few housekeeping items before we get started. Everyone will be on mute during the presentation, but you can ask questions at any time using the GoToWebinar questions option. There's also a chat feature if you'd like to toss in a comment or something that way, and that's fine as well. With 5 to 10 minutes left in the presentation, I will give everyone the ability to unmute themselves if you would like to comment directly or ask a question or for any live discussion, that kind of thing. You'll also get an email from GoToWebinar after the presentation with a link to the recording, and we post all of them on our website, stantec.com, and we'll put a link to that in the chat a little bit later in the presentation. So with that, let's kick it off. Today we're talking about Coagulation 101. It'll be presented by our sector lead for water treatment, Dr. David Pernitsky. And with that, I'll turn it over to David.
All right, thanks everybody. Thanks for joining us. Again, my name is Dave Pernitsky. I'm in Stantec's Calgary office, where we're enjoying the early part of winter. And I'm going to talk today on coagulation. I've done a lot of coagulation troubleshooting over the years at various plants, and it's a pretty basic topic in terms of it's at every water treatment plant, and it doesn't it's not as exciting or glamorous as ozone or advanced oxidation stuff, but it's really something that I think is essential to get the plant running at a baseline. And if your coagulation is off, you're gonna have trouble maintaining compliance, and then nothing else is gonna be able to follow on top of that. So I want to stress right at the beginning, when we talk about poor coagulation, traditionally we thought at coagulation things settle out in the clarifier and monitor your clarifier turbidities, and that's just not the whole picture, right? That's only one indication. What really coagulation, where it really matters, is in the filters. So if your coagulation chemistry is off, that's most likely what's causing high filtered water turbidity, or long filter ripening times, early breakthrough, or just general low unit filter run volumes. So how much water is produced out of your filter in a given filter run. So especially with the 0.3 NTU limits that our regulations have, and our 0.1 NTU targets like the Partnership for Safe Water has, you have to be bang on with the coagulation to meet those. So we're going to talk a lot more about filters than we are about clarifiers today. So if we think about why do we coagulate, there's really two reasons. And the first one is, the classical reason. We're going to condition the raw water particles so that they can be removed by clarification and filtration. So we're going to take away their negative charge, neutralize their charge so that they can be removed. Why we do that is because the particles in turbidity, they're a surrogate for the pathogens that we're trying to remove. So that's that's job one. That's where you're getting your pathogen reduction credits for chemically assisted filtration. The second reason, and one that actually tends to be more important in practice to get things to work well, is that we have to convert all the natural organic matter, all the total organic carbon, that is in that water. We have to convert as much of that as we can to a solid phase so that it can get removed by clarification and filtration. And that might be to remove color. It might be to remove disinfection byproduct precursors. You might be looking to increase your UV transmittance to improve a downstream UV disinfection step. But what you're going to see today is that converting that NOM and satisfying its coagulant demand is a prerequisite to getting everything to work. So our end goal is to make near neutral flock particles that filter well. Okay, so we're going to talk a lot about the charge of the flock particles, because that's really what makes our filters work well. So the critical elements in this, we're going to talk about the chemistry of the contaminants, the particles, and those dissolved organics. We're going to talk about the chemistry of the coagulants, and there's a little, some subtle differences between the different metal salt coagulants that we have, whether they're aluminum based alum, polyaluminum, chloride, or whether they're ferric based. We're going to talk a bit about organic polymers, and then we're going to talk about the solution parameters, and pH is the most important parameter that we're going to talk about today. It just affects absolutely everything. So if we take a look at the chemistry of our particles, there's a whole bunch of different particles we might find. We might get clay particles or some other kind of mineral. There'll be algae particles. There'll be other kinds of organic debris. And what we're concerned about is that they all have some kind of pH-dependent surface chemistry. So if you look in the right-hand side there, this is an example of a clay surface, and you see there's all these aluminum oxides in this clay, and on the surface, on the edge, what's exposed to the water are there some aluminums with some hydroxide groups on them, okay? And you'll find this hydroxide type of chemical group on the surface of most particles, right? They'll be on algae particles, they'll be on leaf debris and everything else that you might have. And this is what happens when the pH changes. If you have a low pH, there's lots of hydrogen ions in solution, these hydrogens tend to stick on the base molecule because there's lots of hydrogens in solution, so your equilibrium principles keep that attached. As the pH increases, you have fewer hydrogen ions in solution, and so to keep equilibrium, there's a tendency for the hydrogens that were attached to the surface to leave and go off in solution. And that leaves us with a surface that has less positive charge or a more negative charge. So at higher pH, all of these particles get more negative. And as the pH decreases, they become less negative. Similar situation with NOM. The natural organic matter in each water supply is unique. It's very complicated. This is a conceptual design or a conceptual sketch of a humic acid type molecule, and it doesn't really matter what it looks like except it's big and it has a lot of different functional groups in there. Hydroxide, carboxylic acids, phenolic, it doesn't matter. From the perspectives of what we need to know, all of these behave generally like hydroxide groups. So just like the particles, they're negative at neutral to high pH, and they're less negative at low pH. So here's a carboxylic acid at low pH. As the pH increases, that hydrogen leaves, and we end up with a negative charge. Same thing with, it could be an amine group with ammonia here. It becomes less positive. So overall, you've got more negative charge at high pH. And then the second thing that we'll talk about is the charge demand of these organics tends to be 10 to 100 times greater than the charge demand that you would see in your water for most waters than from say clay particles. Okay, so if we took an example, if we looked at the particle charge that is on 10 milligrams per liter of suspended solids, and if that had a charge of half a milliequivalent per milligram, we'd have five charge units from the particles. But if we had just 3 milligrams of TOC, and depending on just what exactly that TOC was like, it could have a charge of 10 or maybe 100 milliequivalents per milligram. So the contribution of negative charge from the NOM could be 30 or 300. So we find that rarely does the turbidity control the coagulant dose. The big thing, the big negative charge that consumes coagulants tends to be the amount of TOC or NOM that we have in the water source. Okay, so the dose that we have to add to get things to work primarily, firstly, depends usually on the NOM concentration, and then second, once we've satisfied the charge demand of that NOM, it's the charge on the flock that we end up producing. So there's a couple of things. Most importantly, you need a timely measure of raw water NOM for use in adjusting the coagulant dose. So, you measure turbidity of the raw water online, but fortunately, more and more people are putting something on the front end to measure the organics. Some people have online TOC, other people have online UV absorbance. So you can tell that there's a change in the organic concentration in the raw water, and it may not always coincide with turbidity. It might in the runoff after a storm, but it might not. So if you're not measuring NOM in some way on the front end of the plant, you could get caught by surprise and end up with a coagulant underdose and early filter breakthrough. So if we talk now about the chemistry of the coagulants, it's a little more complicated, but for the metal salt coagulants, when you add something like alum, aluminum sulfate, to the water, it's going to form a series of dissolved species, and it's going to form solid flock particles. And how much of the coagulant ends up being dissolved and how much ends up being in the solid form is pH dependent, and the charge of those dissolved species and the charge of the flock surface is pH dependent. Now, fortunately, the only chemical thing you need to know, the only chemistry that you really need to know from this whole presentation is those dissolves, all those species, the charge is more positive at low pH, okay? So the lower the pH, the more positive charge we get, both in the dissolved species and the flock surface. So that's easy to remember. And, these metal salt coagulants, they generate either aluminum hydroxide or a ferric hydroxide sludge. Organic polymers, on the other hand, they operate through the charged functional groups they have on their big organic backbones. And that charge is largely unaffected by pH, and they generate less sludge. So they have a role. They're more expensive than your metal salt coagulants, but they have a nice role to play in, say, high pH waters when your alum, let's say, is not working great because the pH is pretty high. Some organic polymer, cationic polymer, can be used quite effectively to get that same charge neutralization, and we've got a case study that I'll show you at the end of this. So now we start to get into some a little more complicated diagrams here, but bear with me. What we're talking about here is, for alum, the solubility and then the speciation of those chemicals. So if we look at this graph on the left, you have pH on the x-axis, and you have the log of the aluminum concentration in moles. Okay, so that's not the world's most user-friendly graph, but think of it this way. What this graph shows is at any given pH, let's just take pH 6. If you were to add alum at pH 6, you would find that 10 to the minus 6 would be the dissolved aluminum concentration, and the rest of it would be solid flock particles. So if you drop the pH down to very, very low levels, the amount of dissolved aluminum becomes quite high. And this is why, if you want to do a total aluminum analysis on a water sample in the lab, you add acid and you preserve that sample down at pH 2 so that any solid particles strictly exist in the dissolved form, and you can measure them in your lab. So what this does, this tells us that the minimum solubility, the point at which the maximum amount of flock is produced, happens with alum at 20 degrees at about pH 6.2. And at 5 degrees, the aluminum is actually less soluble, so you get, it's less soluble, so you get more flock produced and lower residual aluminum levels. But the pH at which that occurs is a little bit, maybe 6.6. It's higher than it is at 20 degrees. So if you want to maximize your flock production, and what we'll see here later on is that these pH values of minimum solubility, they tend to be good target points for maximum coagulant effectiveness, but that's going to change seasonally. In the wintertime, you may want to run that coagulant pH at a higher value. The other thing we'll see here is if you're trying to meet residual aluminum targets in your filtered water, it's going to be harder to do that in the summer because the solubility dictates that there's going to be more dissolved aluminum at all conditions at 20 degrees. So most of what we find is flock, and the flock is the most important. This graph, though, just shows you what's happening with the species that happen to be dissolved. And I include this because most of us just think when we add alum, we're adding Al3+. But that's not exactly what you're getting in solution. That aluminum hits or mixes with the water and it hydrolyzes. So the OH ions in water tend to get, or the water molecules that are associated with this, you know, they tend to shed some electrons and stuff, or some hydrogens. So the bottom line, the chemistry gets quite complex, but here's what you need to remember. You're only getting Al3+ at, you know, the very low pHs, right? So pH less than 6, you've got a fair bit of it. pH 5, you've got a lot of it. But if you're coagulating like most of us are between 6 and 7, the dissolved species that's actually doing the work is an aluminum species that only has a charge of +1. And if you're operating up here at pH 7.5, the dissolved species that it's actually in solution is got a -1 charge. So you're not going to get a whole lot of, you're getting a lot less bang for your buck at these higher pHs. I'll show you a graph later on that shows how the flock charge varies, and that's the most important, but this is just very illustrative of that pH effect. Okay, so if we talk about polyaluminum chloride chemistry, we first have to just define a little bit about what it is, because there is no chemical except polymers less understood and you know, more foggy in the world of procuring water treatment chemicals. So we have to remember polyaluminum chloride is an aluminum chloride solution that has been titrated with caustic, and it's titrated under such conditions as temperature, pressure, and mixing considerations that are really important, but it forms an inorganic aluminum 13 polymer with a +7 charge, okay? So it's got a high charge, and that's what it's known for. It's called pre-hydrolyzed because you're taking aluminum and you're adding it with caustic right in the reaction. And if you imagine that, you know, every mole of aluminum has 3 moles of hydroxide, this would be fully neutralized, okay? Or it would be 100% basic. So this is the terminology you'll see in these polyaluminum chlorides. They'll say it's high basicity, it's low basicity, and it refers to the ratio of how much base to how much aluminum, with 100% meaning fully reactive. So you'll see the higher the basicity, the higher that aluminum 13 content, because it's driving this polymerization reaction. But also the higher the basicity, the lower the alkalinity consumption. So alum is a pretty effective acid. It drops the pH quite nicely. But these, because they're, you know, pre-neutralized and they have had some caustic, they drop the alkalinity less. So commercially, we get 20%, generally is kind of low, 40 to 50% is considered medium, 75 plus or minus is considered a high basicity product. And then for reasons unknown to me, very high basicity PaCl, stuff that's around the 85%, is called aluminum chlorohydrate. And no one has yet given me a good explanation for this. And if anyone knows why, other than you know, marketing obfuscation, I've yet to know, so please let me know. These chemicals, these polyaluminum chlorides, they can contain other additives, sulfates, silicates. Some are blended with organic polymers. The strength often varies. Some are, you know, have more aluminum in them than others. So you have to just look at the spec sheet, know what you're dealing with, and then you can optimize things. So with all these choices, the general rule is you want to match the basicity of the product to the raw water alkalinity to give you the best coagulation pH. So if you're, say, on the East Coast of North America and you have a low alkalinity water, but you have a fair bit of organics, and if you needed, say, 30 milligrams per liter of alum, for example, that would consume an awful lot of alkalinity. And you may end up in a situation where if you took your raw water and added that much alum, you'd end up consuming all the alkalinity and your pH would drop to 4 and no flock would form. So in that situation, you might want to consider a higher basicity polyaluminum chloride because it'll consume, 75% of the alkalinity that the alum will. So it might drop your pH less, and then you don't need to add caustic. However, if you're on the West Coast or in a someplace like the Colorado River or the North Saskatchewan River, and you've got a lot of alkalinity, you want to have something that has some acidity so that it can drop the pH into the range in which these coagulants will work best. So there's a lot of testing involved, and we'll just give some examples of how this works in a bit here. So this is that same solubility diagram, just this time with some color. This bright purple is the alum solubility, okay, and this is at 20 degrees. So this shows again 6.2 alum. Alum is very insoluble, and its minimum solubility is there. This is some experimental data from some high basicity polyaluminum chlorides and then this very high aluminum chlorohydrate. And you can see that these chemicals, these are the theoretical lines for the different species. So your aluminum 3+ and 2+ and 1+, these are the monomeric aluminum that you'd expect to see in alum. Here's the theoretical solubility line for that aluminum 13 polymer. That's what your high basicity PaCl tends to follow. So a couple of practical considerations. If you were to add this blue polyaluminum chloride, its pH, a minimum solubility is say 6.6. It's much higher than alum. If you tried to operate at pH 6 with this polyaluminum chloride, you can see that you're not going to get much flock at all. It's going to stay soluble and stay in the dissolved form. So you have to have a different pH range for these products. And we show the high basicity side in blue, the alum in purple. If you had a medium basicity product, the solubility line would kind of fall in the middle of those two. So this again shows the aluminum species in solution. These are the dissolved species, and we're just comparing alum, right? We have this +1 charge existing in the neutral pH zone, but with polyaluminum chlorides, it's this aluminum 13 polymer that dominates in our neutral pH zones. So this is probably one of the reasons why a lot of people have good success with polyaluminum chlorides, is they have more charge neutralization capacity in the pH range we normally use. Now, all of those graphs are good. This is the graph I like the best. I think it's the most useful. This shows us versus pH, the particle charge as measured by Zeta potential. So Zeta potential is just a lab technique that allows us to measure the charge on the flock particles or clay particles or anything. So this shows what we want, because coagulation works by direct interaction of the coagulant chemical with our contaminants, but it also, and probably more dominant, is the production of flock particles and the reaction of contaminants, whether it's NOM or other particles, with the surface of that flock particle. But regardless of how it gets there, after it's reacted with things, it's the charge on the particles that we end up with that's important. So here, this shows you if you added alum and you added it at pH 7, the flock particles formed are between just a little bit higher than +10 millivolts. If you drop the pH to pH 5, so you're in enhanced coagulation range, that particle charge from this experiment was closer to +15. So it gets better as the pH drops, but look what happens to it as the pH increases. It gets really quite bad. So at pH 8, where a lot of people with high alkalinity waters end up, the charge on these particles is not that great. But if you take a look at any of these polyaluminum chlorides, and we have a 25% basicity PAS, polyaluminum sulfate, 33% polyaluminum chloride, then a 67 and an 83%. So the higher the basicity, the stronger the charge. And in this, these experiments are only done between 7 and 9 that I've got up here. But the particle charge from these polyaluminum chlorides is way higher than alum. So again, this just gives you some theory and some lab data that explains what you might have seen in the plant, where these polyaluminum chlorides work better in some cases at higher pHs. So that's the flock charge. Now this is where it gets a little more complicated. We talked about lower basicity polyaluminum chlorides. They depress the pH more, and so we know that lower pH removes more NOM. So if we take a look, what we've got in this first graph is this UV absorbance, the fraction remaining. So the lower down on the graph, the more UV removal we've had, more removal of UV absorbing substances. So circles here are alum. This is milligrams per liter as aluminum, okay? So we're comparing the same thing, not milligrams per liter of product, because the strength of these things can be quite different. But if we take alum at its minimum pH and minimum solubility 6.2, we get very good for this water organics removal. So we're at between 50 and 60% removal of the UV. All of these other graphs, and we'll take the black squares, that's the highest basicity polyaluminum chloride. And if you don't adjust the pH for this water, after coagulant addition, it's somewhere between 7.5 and 7.8. So not in a great range for charge neutralization. And you can see the UV removal is less. If you look at a medium or a low basicity product, they're kind of in the middle. So there is some situations where you can enhance the organics removal by taking that high basicity product and adding some acid and dropping it. So we take, this is the same data shown above, the high basicity PaCl in an unadjusted situation. If we add a little bit of acid to drop it to 7, 6.5, 6.2, even just dropping it to 7 provides pretty much the same organics removal as we had with alum at 6.2. So even though those PaCl still have highly positively charged flock, the NOM removal still requires a lower pH, so you still need to test this. So it's a balance between making sure you get the right basicity of the PaCl, the final pH of coagulation. You got to test it in some jar tests to see what works. Okay, if we just move away from alum and aluminum and look at ferric, ferric is it's a little bit of a different coagulant. It is much less soluble. So you get, before alum was 10 to the minus 6 moles as a minimum solubility. This stuff is 10 to the minus 10. It's just insoluble. It forms flock particles like crazy. We don't have residual iron issues when we coagulate with iron coagulants. The other thing, though, is that the positive species, the really strong positive species like the Fe3+, they exist at a much lower pH than alum did. And now this graph, the bottom one shows the surface charge of iron hydroxide particles, and a neutral product, or neutral flock charge kind of dominates through most of the range. And these positive surface charges don't show up in appreciable concentrations until you're in the mid to low 6s. So that's why a lot of places you won't be able to use ferric coagulants very effectively until you drop that pH down to 6, 6.5 or 6 in some cases. Okay, so ferric is a low pH coagulant if you really want it to be working well. So if we summarize both the coagulant species themselves, the organics, and the particle charge, everything is favorable at low pH. At low pH, our organics are less negative, so they'll take less coagulant to neutralize, and our coagulants have more positive charge power. So low pH is better for coagulation with metal salt coagulants. Okay, so we're looking at keys to controlling coagulation, we have to know how much NOM, and we have to satisfy that charge demand of the NOM. And then we have to know the pH after coagulation. That's going to control our aluminum residuals. It's going to determine the efficiency of organics removal, and it's going to determine the flock surface charge, which in the end is going to affect the clarification and filtration performance. So this is an example of what I've called the coagulant demand, firstly, and then the effective pH. So this graph, again, has milligrams of aluminum, okay? So if you needed to mentally convert that to milligrams of alum, multiply by 11. So 2 milligrams of aluminum is 22 milligrams of dry alum. So this particular water, and we've got electrophoretic mobility, which is kind of like zeta potential. Think of this as particle charge, okay, without getting into all of the voodoo science behind this. 0 is neutral, positive charge above negative charge. So particles start in this particular water. We've got negatively charged particles, and we start to add coagulant. And we're at a fixed pH of 6.2. So we add coagulant and acid or base to maintain 6.2 because this is a lab study. And you can see that the particle charge doesn't really change. We've added coagulant, flock particles are forming, but they're still negatively charged. We add a little more coagulant, we're at 1 as aluminum, say 11 as alum. Not much has changed. For this particular water, at this pH, we neutralize, our flock particles are neutral at, at 1.5 milligrams as aluminum, okay? So this flat part of the curve is a charge demand that you can think of just like chlorine demand. So when you add chlorine, it's reacting with organics, it's doing a lot of stuff. There's a chlorine demand before you see a residual. There is a charge demand with a coagulant before you start to see a charge neutralization effect. So you see that at pH 6.2. This is the exact same water, but this is at pH 7.5. So the charge demand is way higher because the organics, which make up most of the charge demand, are much more negative, and the coagulants are much less positive. So the only one that gets close to neutralizing the particles in this experiment is this, a high basicity, no sulfate polyaluminum chloride. So that high basicity polyaluminum chloride can do the job, but alum is never going to make neutral particles for this water under these pH conditions. So your coagulant selection becomes much more critical at high pH. This graph is kind of the same idea, the same series of experiments, but here are 3 different waters. The water number 1 has a turbidity of 16. It's got 2.5 milligrams of TOC, but the SUVA, which is the amount of the specific UV absorbance, talks about how reactive to coagulation the material is fairly low, okay? So you can see here in that water 1, there's not a lot of reactive organics. We add coagulant, and right away, we get charge neutralization. So the coagulant demand is essentially nothing here, okay? Water 2, low turbidity, very low turbidity, lake water. Again, moderate TOC, but its TOC is much more reactive. The SUVA is 3. Here's where you see that charge demand. And this water, again, low turbidity, water number 3, TOC of 6, very high SUVA. The scales are different here because to fit them all on here, but we've got a charge demand. The curve is pretty flat for like 2 to 3 milligrams of aluminum, twice what it is up here, okay? So the higher the organics, the more that initial charge demand. And this is even at kind of optimum pH conditions. Okay, so given all that kind of background, now we'll get into, the poor coagulation causes poor filter performance. We'll get into the practical aspect. So this is what's going to happen if your coagulant is off. You'll have long ripening times, early filter breakthrough, and your conventional jar tests give you little indication of how filterable your flock is actually going to be. So we need some other measurement. So what I like plants to do when they're starting an optimization is look at that filter UFRV, okay? So it's the water produced, it's the production of the good water. So after ripening and before the end of the run, just divided by the unit area of the filters. So that's either cubic meters per square meter, gallons per square foot, and it allows you to compare filters independent of their loading rate. So a 48-hour filter run might be good, but not if the loading rate is really, really low. It's not producing as much water. And this is just a graph that a plant did from an optimization study. And you can just see here that, they had good unit filter run volumes for a while. They made some changes in their plant, and they had some things going on. And then, you can just see that over time, their unit filter run volumes have dropped. And you wouldn't necessarily see this day to day, but looking at it over a couple of years, you can say, hey, maybe we have drifted away from our optimum coagulation range, and we might need to give it some attention. So when we look at our filters, we're not doing surface straining. Membrane filters work like this. The pore size is small, particles get excluded. What we're doing in media filters, like if you took your granular media filter in your water plant and added no coagulant, the small particles that are in your lake or river water are going to go right through the pore spaces of the media. So we need to neutralize the charge on these particles, and we make them bigger through flocculation and coagulation, but it's this physical chemical attachment to the media that's really going on in a media filter. Okay, so we need these near neutral charge particles to adhere to the grains. Okay, and if they're not attached tightly, they will get released by hydraulic shear as the bed gets full, and you'll end up with that breakthrough if they're not attached well. So that's why we need to make sure that coagulant is optimum to maximize the attachment. We use zeta potential or streaming current as a nice way of measuring that actual flock charge. And there's a whole bunch of studies where people have shown, these are the ranges of zeta potential or particle charge that different real plants have found where the plant actually works good in practice. So we don't have to be at zero. There's a lot of plants here that show that, at -7 or -5, things are working well. So here's I really like the zeta potential tool, and here's a bit of an example as to how it can be used. So this is a case study. We had a direct filtration plant. They were having some challenges meeting their 0.3 filtered water turbidity limit if they started, if they cranked the coagulant up so that the filters would ripen and they'd meet 0.3, they had a lot of solids, high head loss, and short filter runs. But if they dropped the coagulant dose to try to minimize the amount of flock going on the filters, they'd get early breakthrough and short runs. So they had this real challenge trying to keep up in the summer with demands. They couldn't produce enough water to keep up with the backwashes and demand. So this was an early example. This was published at an AWWA conference, about 10 years ago. We went in and said, hey, we did some jar tests at various coagulant doses and just measured the zeta potential. And we saw, with the coagulants that they're using and then some other ones, they've got a pretty big charge demand here. The current plant was trying their best to operate at, say, 1.7 milligrams as aluminum, and we're like, no, and you can see that we're a long ways away from neutralization. So they knew that if they increased the coagulant dose, they were just going to have too many solids and gum up the filters. So the thought was, let's evaluate some cationic polymers that might be able to raise that pH up for them. So we did some jar tests with a particular polymer. We kept their baseline polyaluminum chloride dose and just started adding different amounts of polymer to see what would get us to roughly -5. And you can see it took 2 milligrams of polymer, cationic polymer, just to even move the needle on the charge. And we saw, okay, about 4 milligrams per liter on bench with jar tests looks like it should work. So they got a temporary polymer dose system, kept their baseline polyaluminum chloride, and then at full scale, they started adding very slowly different amounts of polymer. And they were quite concerned. 4 milligrams was a lot. It was higher than most people had used, but you can see that unit filter run volume, it maximized at 4 milligrams per liter just in the bench, just like it did in the bench. So we're like, okay, we got near neutral particles, things are working, we're doing the best we can with this particular plant. Okay? So there's nice correlation between zeta potential and performance. This is some data from another plant that shows that you really need good data analysis to pick up on some subtle changes in the filter performance. So we use zeta potential again, and we used unit filter run volume as the measurement. So these blue lines or blue dots are the unit filter run volume. So, you know, at this particular dose of ferric, anything from whatever this is, let's say 27.5 up to 30, filter production was really good. But if we drop that down by just a couple milligrams per liter down to 25, filter performance, went completely bad. We couldn't get these filters to ripen with just 2 or so milligrams per liter. And you can see, there's a lot of scatter in the zeta potential data over all these tests. But we sort of said, okay, if you want to be above -7 for this particular plant, if you can control your coagulation to that, you'll stay out of the danger zone. And again, this unit filter run volume, that is the parameter that you measure, because it accounts for everything. No matter what you make changes to the coagulant dose or the flock mixer speed, if it doesn't show up as a difference in unit filter run volume, maybe it's not important. So the last thing I'll talk about here is filter and flock aids, because they're quite different. We've talked about this charge neutralization idea, that you've got to get neutrally charged particles. But there are certain situations when the flock particles might be neutrally charged, but you're still getting poor performance, either in your clarifier or your filters. So those particles may be too small. They may be too small to settle, right? You may need that heavy, big flock to work in a clarifier, or they may be too fragile to be retained in filters. And lime softening plants are particularly susceptible to that. You get neutral lime softening particles, mag hydroxide and calcium carbonate, but they're very small. They don't get retained well in filters. So in those situations, sometimes a high molecular weight polymer can get used at fairly low doses, and it enlarges and strengthens the flock so it sticks in the filter better. And you've got to balance the particle retention and the head loss. Okay, so this graph, this is a Scada plot, so it's naturally busy. But if you take a look at the black line is filter turbidity, the blue line is the head loss, and the green line is filter flow. So the filter flow is relatively constant for this test. And here we started off a plant, 0.3 NTU is our target. These filters with no filter aid were starting up, and the filter ripening took a long time, and filter ripening was almost immediately followed by the start of breakthrough. And we knew this was going to happen. This was during startup of a plant. We hadn't got the filter aid dose dialed in yet. So now we start with a high molecular weight, filter aid, very low doses. You can see that, okay, now it starts to clean up and we get less noise in this, but we're still breaking through. Increase it a little bit more. Okay, ripening is happening and we're holding down for a little bit better. Finally, at a dose, of 0.15, at the filters ripen, whoops, and they ripen, they stay ripened. And the only other thing you'll see is the head loss curve gets increasingly steep. So you're balancing low turbidity with head loss. If you overdose the filter aid, the head loss goes way up and your filter runs get really short. And so there's a bit of balance, and unit filter run volume is the metric that you want to do this analysis. Okay, so in summary, we know that the natural organic matter, or TOC concentration, is going to control the coagulant dose. So you have to monitor it, and you have to expect, if you've got a lot of TOC, you're going to need a lot of coagulant. We know now that alum works best at pH less than 7. You can get it to work in the mid-7s, but lower is definitely better. Polyaluminum chlorides, they're going to work best at a pH that's greater than 6.5. Often between 6.5 and 7 is where they work the best. Ferric coagulants best at pH less than 6.5. We really think that measuring zeta potential or streaming current is the best way to control your coagulant dose. Figuring out a correlation for your plant, when my zeta potential is more neutral than -7 or -5, or whatever it is for your plant, that's knowing that allows you to keep your coagulant dose adjusted to a quantitative number under changing water quality conditions. And streaming current can be used the same way. And then benchmark that performance with unit filter run volumes rather than anything else, because it's the best metric to show the overall performance of the plant. Okay, there's a bunch of references here for what I talked about, and I think we still have some time for questions.
We sure do. Thank you, David. Very interesting. There's a few questions that have come in here, so let's start off here. First off, can you please explain how Zeta charge is actually measured in the water?
Okay, so unfortunately, I don't have a graphic for this, and you can't see my hands moving. So Zeta potential measures the movement of particles in response to an electric field. So very simplistically, if we used an old-fashioned Zeta meter, we'd have a positive electrode at one side of a sample cell and a positive on one side and a negative on the other side. You'd be watching these particles through a microscope. You turn on the DC current, and all the negative particles would slowly drift towards the positively charged electrode. And you would be watching through this microscope, and these particles would move across a micrometer, and you'd time them how long they took. So one of those graphs showed electrophoretic mobility, and it was micrometers per second divided by volts per centimeter. So if you turned up the DC current, the particle would move faster. So it's the micrometers per second, the velocity, over the electric field strength, and using a whole bunch of complicated equations that I haven't looked at since my PhD, it gives you that effective particle charge. Modern instruments use laser light diffraction to measure the change in velocity. So a modern Zeta meter, you put the sample in a cell and you hit a button, the lasers come on, the power starts being oscillated from positive to negative, and the particles move back and forth, and it measures it. So that's the theory behind it, if that answers that question.
I'm going to assume it does because I can't reply otherwise. All right, another question. How is SUVA measured or calculated?
Yeah, so SUVA is the specific UV absorbance, and how it's measured, what it is in detail. UV light, so specific UV absorbance. So you take your UV absorbance, and that's typically measured as, whatever, 0.1 absorbance units per centimeter, and you divide that, you normalize it by the dissolved organic carbon in milligrams per liter, and then we multiply it by 100 so that we get numbers like 2 or 3 rather than 0.02 or 0.03. But what's important, like if you Google SUVA for water treatment, that equation will come up. But we know that UV light absorbs, carbon double bonds absorb UV light. And the higher the molecular weight of a particular organic compound, the more double bonds. So the higher the UV compared to the DOC, or the dissolved organic carbon, the more double bonds you have. And the more double bonds you have indicates higher molecular weight. And we know it's that fraction of the organic stuff that is most reactive with coagulants. So you can't change the SUVA of your water, you're stuck with the water you get. But if you notice that the SUVA changes between, say, the winter and the summer or after a storm, you can expect that you might have to add more coagulant for a given milligram per liter of TOC than you would under different conditions. And some of the references, if you look up the references, you'll find some good ones that show you how to calculate SUVA.
Okay, great. We're getting just a heads up, Dave. We're getting a lot of questions here, so if we can't get to all of them, we will follow up via email and provide a written answer. All right, next one. Would you say that plants treating low alkalinity and low pH waters do not really have a gain from using metal salt polymers? as long as they have a good control of the coagulation pH.
Okay, you say plants treating low alkalinity, and low pH waters don't have a gain from using metal salt.
As long as they have a good control of their coagulation
Yeah.
pH.
Well, that's a good question. So I've seen a number of different things, and I think the answer to that question is yes, if they have good control of the coagulation pH. So you know what all this comes down to is there's no magic ingredients. And so when I recommend that, in addition to all the jar tests that you do for treatment effectiveness, you should also do an economic effectiveness. So if you've done the work and you're operating with alum plus caustic, and you're getting good removal of your organics, and you're getting good filter performance, so whether you measure Zeta potential or not, your plant is operating well, you can do that with alum and caustic, or you can do that with high basicity polyaluminum chloride and less caustic, or you could maybe do it with a low dose of alum plus cationic polymer plus less caustic. You've got, in your jar test regime, you look at those three scenarios. You may use Zeta potential as a way of comparing three unequal things, but then you should do the economics and say, what does this actually cost me in terms of those polyaluminum chlorides and organic polymers are more expensive. So oftentimes you can get to a more economical solution with old-fashioned alum and old-fashioned caustic. So that's a long answer to the question, but yeah, there's no reason, if it's economically favorable, there's no advantage to using the aluminum polymer coagulants if old-fashioned alum and old-fashioned caustic are doing the job. That's a good question.
Okay. Yeah, good. Does a ballast like sand ever contribute to charge demand?
No, it doesn't. The Actiflow or the Comag, the things that have those ballasts, again, the charge of those sand or magnetite particles is a whole lot lower than the charge demand for many of the organics. So I guess there will be some charge demand, but it's going to be low. So it's not going to be really an important parameter for you.
All right. Is jar testing always necessary to select a proper coagulant? Are there parameters you can use to predict the best coagulant use and forego jar testing?
Yeah, I think you can, and it depends on the situation. So the first part, there are some great water chemistry tools out there, so that we know that you need to be you need to be in the low 7s or even below that, for good performance. And so you can estimate, you can say, all right now I'm just making up numbers, I'm using 100 milligrams of alum, and that takes me down to pH 7. And so if I used, if I wanted to drop the pH, let's say it was 100 milligrams of alum and pH 7.5, and things aren't working great. Well, what could I do? I know that I can, drop the pH with some acid, and you could, if you have some titration data or just some water pro or calculation estimates. I know alum, 1 milligram of alum consumes 0.5 milligram of alkalinity, so my pH is going to drop. So you can do a bunch of this desktop stuff, and you can say, it's a 50% basicity polyaluminum chloride, so that's only going to drop the pH half as much. So you can do a lot of work on the desk and say, will this might work or this might not work. And then, you can go in and do jar tests, or, if you have some tools at your plant, like, a Zeta potential or a streaming current, you can go direct. The other thing I've seen is that even now when we own, Stantec, we have a Zeta potential analyzer and we lug it around, and we don't do a full 20-minute flocculation, 30-minute settling, long drawn out jar test. We do a lot of screening work where we say, we know that we need to be around -5. We might do some grab samples in the plant and say, oh yeah, this plant's running at -7 Zeta potential and things are working pretty well. So, we'll throw some coagulants in a beaker very quickly, rapid mix them, measure Zeta potential, and very quickly we get an idea of what's most likely to work without following the old-fashioned formal jar test procedure. So I encourage plants, once they know what's going on, to take those kinds of shortcuts. You have to make sure, like anything else, there's probably a disclaimer. You have to know what you're doing before you take those shortcuts. But yeah, they're completely legitimate if you've got the backup.
Okay, looks like we've got 3 more, Dave. We can try to get through these in the next 4 minutes. Can we use TOC instead of NOM to estimate the coagulant dose?
Oh yeah, absolutely. So total organic carbon or UV absorbance are both, tools to estimate the NOM that's going to influence coagulation. So yeah, that's what you have to rely on is one of those two. And whether you use TOC or UV absorbance is a little bit site specific, and it's a little bit, and whether you do it online or grab samples, those are kind of choices that are dictated by your budgets, and if you've got good instrument techs to keep those things calibrated and everything. And I kind of used UV and TOC and NOM kind of interchangeable through the presentation, but they're all telling us the same thing.
Okay. Is a filter turbidity target of 0.1 NTU achievable on all plants, providing coagulation is optimized?
Well, probably. If the plant has, if it's a well-designed and well-maintained plant, then there's no reason why you can't get to 0.1 NTU. That's what AWWA and the Partnership for Safe Water program really would like you to do. And there's great backup data that says the lower the turbidity, the lower your risk of pathogens and things. But if you have a direct filtration plant that was designed in the 1980s when the regulation was 0.5 NTU and the TOC is high, like that case study that we showed, that extra coagulant that you need to get you down to 0.1 may cause you head loss problems that you didn't anticipate when the plant was designed. So in that situation, it's going to be tough. And then maybe the other thing to consider is you may end up the coagulant dose may be really tight, or you have to add more acid to get down to that optimum. And so there may be some cost implications with going down to 0.1 compared to 0.3. But we don't see, the standard, dual media filter, clarifier, dual media filter can be optimized to make 0.1. There's no inherent limitations in that technology that would stop you from doing that.
Great. All right. Final question here. Do you have an explanation for the variability in Zeta potential results observed in your slides?
Oh, I have from trying to figure out the variability. That is a very interesting question. And this is a reality. I'm going to go back to this slide. There is variability in this was data that was taken, grab samples from an operating pilot plant over a couple of weeks, and each of these data points represents three measurements. You took a sample and you put it in the instrument, you'd set the instrument up to do 3 replications. And yeah, you know what? We get some spread here from day to day. And I do not have a good explanation for this. The more, what we found was the more the operator did the zeta potential measurement, the tighter the data got. But this is real data, and I've seen other plants and other people have done experiments where, yeah, this kind of variation isn't unusual. So, you know, when we say we have a target, like in this graph of -7, we don't, it's not -7 plus or minus 0.2. It's, in fact, some of the plants we have, or that I know of, that have used zeta potential a lot, they say, yeah, as long as we're between, -5 and +5, or -5 and 0, or -7 to -3, things work. So yeah, that is a fact of life. And I don't have a good explanation. After doing this a long time, I don't have a good explanation, but it's a reality.
All right, great. Well, we're at time. Thank you, everybody that's still on, for all the great questions. And thank you, David, for the awesome presentation. And we hope to see you on an upcoming webinar. You'll all get certificates of attendance you can submit for PDHs. And we will post this presentation on our website if you'd like to share it with your colleagues. With that, I'll say have a good day.
Thanks, everybody.